Infrared spectroscopy is the spectroscopy that deals with the infrared region of the electromagnetic spectrum, that is light with a longer wavelength and lower frequency than visible light. It covers a range of techniques, mostly based on absorption spectroscopy. As with all spectroscopic techniques, it can be used to identify and study chemicals. For a given sample which may be solid, liquid, or gaseous, the method or technique of infrared spectroscopy uses an instrument called an infrared spectrometer to produce an infrared spectrum. A basic IR spectrum is essentially a graph of infrared light absorbance on the vertical axis versus frequency or wavelength on the horizontal axis. Typical units of frequency used in IR spectra are reciprocal centimeters, abbreviated as cm1. Units of IR wavelength are commonly given in microns, abbreviated as I1/4 m, which are related to wave numbers in a reciprocal way. A common laboratory instrument that uses this technique is a Fourier transform infrared spectrometer. Two-dimensional IR is also possible as discussed below. The infrared portion of the electromagnetic spectrum is usually divided into three regions. The near, mid and far infrared, named for their relation to the visible spectrum. The higher energy near IR, approximately 14,000 euro 4,000 ACMA1 can excite overtone or harmonic vibrations. The mid-infrared, approximately 4,000 euro 400 ACMA1 may be used to study the fundamental vibrations and associated rotational vibrational structure. The far infrared, approximately 400 euro 10 ACMA1, lying adjacent to the microwave region, has low energy and may be used for rotational spectroscopy. The names and classifications of these subregions are conventions, and are only loosely based on the relative molecular or electromagnetic properties. Theory. Infrared spectroscopy exploits the fact that molecules absorb specific frequencies that are characteristic of their structure. These absorptions are resonant frequencies, that is, the frequency of the absorbed radiation matches the transition energy of the bond or group that vibrates. The energies are determined by the shape of the molecular potential energy surfaces, the masses of the atoms, and the associated vibronic coupling. In particular, in the Born-Oppenheimer and harmonic approximations, that is when the molecular Hamiltonian corresponding to the electronic ground state can be approximated by a harmonic oscillator in the neighborhood of the equilibrium molecular geometry, the resonant frequencies are associated with the normal modes corresponding to the molecular electronic ground state potential energy surface. The resonant frequencies are also related to the strength of the bond and the mass of the atoms at either end of it. Thus, the frequency of the vibrations are associated with a particular normal mode of motion and a particular bond type. Number of vibrational modes. In order for a vibrational mode in a molecule to be IR active, it must be associated with changes in the dipole. A permanent dipole is not necessary, as the rule requires only a change in dipole moment. A molecule can vibrate in many ways, and each way is called a vibrational mode. For molecules with n number of atoms in them, linear molecules have 3 or 5 degrees of vibrational modes, whereas nonlinear molecules have 3 or 6 degrees of vibrational modes. As an example, H2O, a nonlinear molecule, will have 3 A3 or 6 A equals A3 degrees of vibrational freedom, or modes. Simple diatomic molecules have only one bond and only one vibrational band. If the molecule is symmetrical, for example N2, the band is not observed in the IR spectrum, but only in the Raman spectrum. Asymmetrical diatomic molecules, for example CO, absorb in the IR spectrum. More complex molecules have many bonds, and their vibrational spectra are correspondingly more complex, that is, big molecules have many peaks in their IR spectra. The atoms in a CH2X2 group, commonly found in organic compounds and where X can represent any other atom, can vibrate in 9 different ways. 6 of these involve only the CH2 portion, symmetric and antisymmetric stretching, scissoring, rocking, wagging and twisting, as shown below. These figures do not represent the recoil of the C atoms, which, though necessarily present to balance the overall movements of the molecule, are much smaller than the movements of the lighter H atoms. Special effects. The simplest and most important IR bands arise from the normal modes, the simplest distortions of the molecule. In some cases, overtone bands are observed. These bands arise from the absorption of a photon that leads to a doubly excited vibrational state. Such bands appear at approximately twice the energy of the normal mode. Some vibrations, so-called combination modes, involve more than one normal mode. The phenomenon of Fermi resonance can arise when two modes are similar in energy. Fermi resonance results in an unexpected shift in energy and intensity of the bands, etc. Practical IR spectroscopy. The infrared spectrum of a sample is recorded by passing a beam of infrared light through the sample. When the frequency of the IR is the same as the vibrational frequency of a bond, absorption occurs. Examination of the transmitted light reveals how much energy was absorbed at each frequency. This can be achieved by scanning the wavelength range using a monochromator. Alternatively, the whole wavelength range is measured at once using a Fourier transform instrument, and then a transmittance or absorbance spectrum is generated using a dedicated procedure. Analysis of the position, shape and intensity of peaks in this spectrum reveals details about the molecular structure of the sample. This technique works almost exclusively on samples with covalent bonds. Simple spectra are obtained from samples with few IR-active bonds and high levels of purity. More complex molecular structures lead to more absorption bands and more complex spectra. The technique has been used for the characterization of very complex mixtures. Spectra issues with infrared fluorescence are rare. Sample preparation. Gaseous samples require a sample cell with a long path length to compensate for the diluteness. The path length of the sample cell depends on the concentration of the compound of interest. A simple glass tube with length of 5 to 10 cm equipped with infrared transparent windows at the both ends of the tube can be used for concentrations down to several hundred ppm. Sample gas concentrations well below ppm can be measured with a white cell in which the infrared light is guided with mirrors to travel through the gas. White cells are available with optical path length starting from 0.5 m up to 100 meters. Liquid samples can be sandwiched between two plates of a salt. The plates are transparent to the infrared light and do not introduce any lines onto the spectra. Solid samples can be prepared in a variety of ways. One common method is to crush the sample with an oily mulling agent in a marble or agate mortar, with a pestle. A thin film of the mull is smeared onto salt plates and measured. The second method is to grind a quantity of the sample with a specially purified salt finely. This powder mixture is then pressed in a mechanical press to form a translucent pellet through which the beam of the spectrometer can pass. A third technique is the cast film technique, which is used mainly for polymeric materials. The sample is first dissolved in a suitable, non-hygroscopic solvent. A drop of this solution is deposited on surface of KBRNaCl cell. The solution is then evaporated to dryness and the film formed on the cell is analyzed directly. Care is important to ensure that the film is not too thick, otherwise light cannot pass through. This technique is suitable for qualitative analysis. The final method is to use microtomy to cut a thin film from a solid sample. This is one of the most important ways of analyzing failed plastic products, for example, because the integrity of the solid is preserved. In photoacoustic spectroscopy, the need for sample treatment is minimal. The sample, liquid or solid, is placed into the sample cup, which is inserted into the photoacoustic cell, which is then sealed for the measurement. The sample may be one solid piece, powder or basically in any form for the measurement. For example, a piece of rock can be inserted into the sample cup and the spectrum measured from it. It is important to note that spectra obtained from different sample preparation methods will look slightly different from each other due to differences in the sample's physical states. Comparing to a reference. To take the infrared spectrum of a sample, it is necessary to measure both the sample and a reference. This is because each measurement is affected by not only the light absorption properties of the sample, but also the properties of the instrument. The reference measurement makes it possible to eliminate the instrument influence. Mathematically, the sample transmission spectrum is divided by the reference transmission spectrum. The appropriate reference depends on the measurement and its goal. The simplest reference measurement is to simply remove the sample. However, sometimes a different reference is more useful. For example, if the sample is a dilute solute dissolved in water in a beaker, then a good reference measurement might be to measure pure water in the same beaker. Then the reference measurement would cancel out not only all the instrumental properties, but also the light-absorbing and light-reflecting properties of the water and beaker, and the final result would just show the properties of the solute. A common way to compare to a reference is sequentially: first measure the reference, then replace the reference by the sample and measure the sample. This technique is not perfectly reliable. If the infrared lamp is a bit brighter during the reference measurement, then a bit dimmer during the sample measurement, the measurement will be distorted. More elaborate methods, such as a two-beam setup, can correct for these types of effects to give very accurate results. The standard addition method can be used to statistically cancel these errors. FTIR. Fourier transform infrared spectroscopy is a measurement technique that allows one to record infrared spectra. Infrared light is guided through an interferometer and then through the sample. A moving mirror inside the apparatus alters the distribution of infrared light that passes through the interferometer. The signal directly recorded, called an interferogram, represents light output as a function of mirror position. A data processing technique called Fourier transform turns this raw data into the desired result, light output as a function of infrared wavelength. As described above, the sample's spectrum is always compared to a reference. There is an alternate method for taking spectra, where one wavelength at a time passes through the sample. The dispersive method is more common in UV-vis spectroscopy, but is less practical in the infrared than the FTIR method. One reason that FTIR is favored is called Felget's advantage, or the multiplex advantage. The information at all frequencies is collected simultaneously, improving both speed and signal-to-noise ratio. Another is called Jacquinot's throughput advantage. A dispersive measurement requires detecting much lower light levels than an FTIR measurement. There are other advantages, as well as some disadvantages, but virtually all modern infrared spectrometers are FTIR instruments. Absorption bands. IR spectroscopy is often used to identify structures because functional groups give rise to characteristic bands both in terms of intensity and position. The positions of these bands is summarized in correlation tables as shown below. Wave numbers listed in CMA 1. Badger's rule. For many kinds of samples, the assignments are known, that is which bond deformation, S, are associated with which frequency. In such cases further information can be gleaned about the strength on a bond, relying on the empirical guideline called Badger's rule. This rule states that the strength of a bond correlates with the frequency of its vibrational mode. That is, increase in bond strength leads to corresponding frequency increase and vice versa. Uses and applications. Infrared spectroscopy is a simple and reliable technique widely used in both organic and inorganic chemistry, in research and industry. It is used in quality control, dynamic measurement, and monitoring applications such as the long-term unattended measurement of CO2 concentrations in greenhouses and growth chambers by infrared gas analyzers. It is also used in forensic analysis in both criminal and civil cases, for example in identifying polymer degradation. It can be used in detecting how much alcohol is in the blood of a suspected drunk driver measured as 1/10,000 grams per milliliter equals 100 I 1/4 gram per milliliter. A useful way of analyzing solid samples without the need for cutting samples uses ATR attenuated total reflectance spectroscopy. Using this approach, samples are pressed against the face of a single crystal. The infrared radiation passes through the crystal and only interacts with the sample at the interface between the two materials. With increasing technology in computer filtering and manipulation of the results, samples in solution can now be measured accurately. Some instruments will also automatically tell you what substance is being measured from a store of thousands of reference spectra held in storage. Infrared spectroscopy is also useful in measuring the degree of polymerization in polymer manufacture. Changes in the character or quantity of a particular bond are assessed by measuring at a specific frequency over time. Modern research instruments can take infrared measurements across the range of interest as frequently as 32 times a second. This can be done whilst simultaneous measurements are made using other techniques. This makes the observations of chemical reactions and processes quicker and more accurate. Infrared spectroscopy has also been successfully utilized in the field of semiconductor microelectronics. For example, infrared spectroscopy can be applied to semiconductors like silicon, gallium arsenide, gallium nitride, zinc selenide, amorphous silicon, silicon nitride, etc. The instruments are now small, and can be transported, even for use in field trials. In February 2014, NASA announced a greatly upgraded database, based on IR spectroscopy, for tracking polycyclic aromatic hydrocarbons in the universe. According to scientists, more than 20% of the carbon in the universe may be associated with PAHs, possible starting materials for the formation of life. PAHs seem to have been formed shortly after the Big Bang, are widespread throughout the universe, and are associated with new stars and exoplanets. Isotope effects: the different isotopes in a particular species may give fine detail in infrared spectroscopy. For example, the O stretching frequency of oxymotionin is experimentally determined to be 832 and 788 µ1 for I1/2, 16O and I1/2, 18O, respectively. By considering the O bond as a spring, the wave number of absorbance, I1/2, can be calculated. Where K is the spring constant for the bond, c is the speed of light, and I1/4 is the reduced mass of the O-B system. Is the mass of atom. The reduced masses for 16O and 18O can be approximated as 8 and 9 respectively. Thus, where is the wave number? Wave number equals frequency/speed of light. The effect of isotopes, both on the vibration and the decay dynamics, has been found to be stronger than previously thought. In some systems, such as silicon and germanium, the decay of the antisymmetric stretch mode of interstitial oxygen involves the symmetric stretch mode with a strong isotope dependence. For example, it was shown that for a natural silicon sample, the lifetime of the antisymmetric vibration is 11.4 picoseconds. When the isotope of one of the silicon atoms is increased to 29 C, the lifetime increases to 19 picoseconds. In similar manner, when the silicon atom is changed to 30 C, the lifetime becomes 27 picoseconds. Two-dimensional IR, two-dimensional infrared correlation spectroscopy analysis is the application of 2D correlation analysis on infrared spectra. By extending the spectral information of a perturbed sample, spectral analysis is simplified and resolution is enhanced. The 2D synchronous and 2D asynchronous spectra represent a graphical overview of the spectral changes due to a perturbation as well as the relationship between the spectral changes at two different wave numbers. Nonlinear two-dimensional infrared spectroscopy is the infrared version of correlation spectroscopy. Nonlinear two-dimensional infrared spectroscopy is a technique that has become available with the development of femtosecond infrared laser pulses. In this experiment, first a set of pump pulses is applied to the sample. This is followed by a waiting time during which the system is allowed to relax. The typical waiting time lasts from 0 to several picoseconds, and the duration can be controlled with a resolution of tens of femtoseconds. A probe pulse is then applied, resulting in the emission of a signal from the sample. The nonlinear two-dimensional infrared spectrum is a two-dimensional correlation plot of the frequency I per mil1 that was excited by the initial pump pulses and the frequency I per mil3 excited by the probe pulse after the waiting time. This allows the observation of coupling between different vibrational modes. Because of its extremely fine time resolution, it can be used to monitor molecular dynamics on a picosecond time scale. It is still a largely unexplored technique and is becoming increasingly popular for fundamental research. As with two-dimensional nuclear magnetic resonance spectroscopy, This technique spreads the spectrum in 2 dimensions and allows for the observation of cross-peaks that contain information on the coupling between different modes. In contrast to 2D NMR, nonlinear 2-dimensional infrared spectroscopy also involves the excitation to overtones. These excitations result in excited state absorption peaks located below the diagonal and cross peaks. In 2D NMR, 2 distinct techniques, COSY and NOESY, are frequently used. The cross peaks in the first are related to the scalar coupling, while in the latter they are related to the spin transfer between different nuclei. In nonlinear 2-dimensional infrared spectroscopy, analogues have been drawn to these 2D NMR techniques. Nonlinear 2-dimensional infrared spectroscopy with zero waiting time corresponds to COSY, and nonlinear 2-dimensional infrared spectroscopy with finite waiting time allowing vibrational population transfer corresponds to NOESY. The COSY variant of nonlinear 2-dimensional infrared spectroscopy has been used for determination of the secondary structure content of proteins. See also, references. External links, infrared gas spectroscopy, a useful GIF animation of different vibrational modes. shu.ac.uk, Illustrated Guide to Basic IR Spectra Interpretation, Infrared Spectroscopy for Organic Chemists, Organic Compound Spectrum Database.